Swayam Prabha. Digital India. Educated India.
So we'll continue with numbers, and this clip is about a very important concept called GCD, or Greatest Common Divisor. And this would let you answer this question we had in the beginning about the Skippy clock, which has some number of hours on the dial, and the needle moves some number of hours at a time. And the question was, which all numbers will the needle reach? So in this example, it was 13, and the needle moves 2 at a time. And we went around the clock and saw that it actually reaches every number. And the question is, in general, when does that happen? Or if it doesn't happen, where all does it reach? So I'll not answer this question exactly, but I'll tell you something that'll let you solve this problem yourself. All right, so the concept we need is related to divisibility. So this we already defined earlier. So the concept of divisors, right? So for a number like 12, there are a bunch of numbers all within the range plus minus 12, so a set of finite numbers, which are the divisors of this number. So we already saw what divisors or factors are. Now we'll talk about common factors between two integers. So for two integers a and b, and you could think of them as positive integers throughout this lecture. So I'll call m a common divisor of a and b if m divides a and m divides b. So it is a factor of a and a factor of b. It's a divisor of a and a divisor of b. That's when I call it a common factor or a common divisor. And GCD is the greatest common divisor, which means the largest among all the common divisors of a and b. Okay, that's a very simple definition then. And it's defined for all pairs AB which are not 0, 0. So one of them could be 0, but both cannot be 0. So it's a simple definition, but first we have to make sure it is well defined, because what we have defined is largest in some subset. And there are a couple of ways this definition may not make sense. If that set of integers we're talking about is empty, then there is no largest element there. Similarly, if that set is infinite, and infinite with larger and larger numbers, then it need not have a greatest greatest element. So for every element in the set, there could be a larger element. Okay. Thankfully, GCD definition doesn't have any of these problems. The set we are talking about, the common divisors of A and B, is a finite set, and it's not empty. It's not empty because one divides every number. So one divides A and one divides B. So it is there in the set of common divisors. And the set is not infinite because we can put an upper bound on what the largest element there could be. In fact, an upper bound is so here if A, suppose A and B are both not 0, then we can say this, right? Say A is smaller than B, A is less than or equal to B, then the divisors of A are all less than or equal to A in absolute value, and therefore the common divisors are all to be less, or have to be less than or equal to A. So that's an upper bound on the set of common divisors. That no common divisor can be larger than either of them. Okay, there's one exception, of course, if one of them is 0, and we'll get to that in a second. But the point is that in any case, there's a finite set and non-empty set, so it has the greatest element. So the set of common divisors of two numbers is finite and non-empty, so the GCD is well defined. as long as both A and B are not 0. Here's an example. So devices of 12, we already had this example in the previous slide. 1, 2, 3, 4, 6, and 12, positive and negative. And devices of 18 are 1, 2, 3, 6, 9, and 18. And the common devices of these two numbers are 1, 2, 3, and 6. And therefore the GCD is the largest among them, and that is 6. Okay. So the one exception I mentioned is about when one of A or B are 0, but here's a more general thing actually that will be useful to know. So if A divides B, so if, when we're talking about two numbers A and B, if one of them divides the other, then the GCD is this divisor, the one that divides the other, right? So if A divides B, then the GCD is A, or absolute error of A is negative. And why is that? Because all the devices of A are also devices of B. So in particular, and the largest among them is absolute value of A, right? So that would be the greatest common divisor. In particular, A divides 0, or every element, every non-zero element, every element divides 0, and if A is not 0, then GCD of A comma 0 is the common devices of A and 0. Since 0 has all devices, these are the common devices of, these are the devices of A, and the greatest among them is A, right? So this is because A divides 0. So always when A divides B, we just argued that the GCD is A. A special case of that is when that B is equal to 0. And in this case, A shouldn't be 0 because otherwise it's GCD of 0, 0, which is not defined. All right, so that is the definition of GCD. By the way, this is what I mentioned here. If one of A or B is 0, then it's no longer true that the GCD is in the range 1 to minimum, because its minimum becomes 0. In this case, it's actually just the other number. So if B equal to 0, then GCD is A. Here is a kind of a way to picture GCD. So imagine we are interested in GCD of 8 and 12 here. Imagine a grid of size 12 by 8. Okay, so it's a grid of squares, say unit length, and there are 8 squares going this way and 12 squares going this way. So it's an 8 by 12 grid. Way to think of common factor is that I could take, so D, a number D is a common factor. If I could take a D by D square tile, so D will divide, D divides 12 and D divides 8, right? So I'll be able to tile row by row and fill fill every row exactly, and then also the columns will line up exactly. So that's what a common divisor is. It's a size of a square tile which can perfectly tile this A by B rectangle. And GCD then is the largest such tile. Okay, so here is an example of a common factor. It's a 2 by 2 square, 2 by 2 tile, and it can perfectly tile the rectangle, but that's not the greatest common divisor. Here is a 4 by 4 tile which can also do the job, and that is the GCD here, the largest such square tile. Okay, so that's 4. It's here's a simple useful fact we'll use shortly. If I give you two numbers A and B, their common divisors are exactly the same as the common divisors of A and B plus A, or even B plus NA for any integer n. Okay, or stated another way, for every integer x, x is in this set, so x divides A and x divides B, if and only if x is in this set, so it divides A and it divides B plus NA. So it's something you should verify. In fact, it's enough to show this in one direction, and you should be able to argue that in the other direction also it holds, because if you think of this as B prime, this is just B prime minus NA. So if you show it in one direction, you can use it to argue both directions. This is something you should do yourself. But just remember this, and we'll use this in a bit. Okay. And in particular, so since the common devices themselves are the same, in particular, the GCD of A and B is the same as GCD of A and B plus NA. N could be negative also. And in particular, so we'll see this, GCD of two numbers A and B is the same as GCD of A and R, where R is the remainder of B when divided by A. So B can, if you write B as AQ plus R, so R is just B minus AQ. And that fits this description, right? It is, take N as minus Q, R is just B plus NA. So GCD of AB is the same as GCD of AR, and where this R is the remainder, as we talked about in the quotient and remainder theorem. Okay, so this is going to be what we are going to use to give an algorithm for finding GCD of two numbers. So we're going to work with positive integers here. Yeah, so the goal, so I'll just describe it pictorially rather than write down the algorithm, which you can find in the textbook. Your goal is to find the largest square tile that will perfectly tile this rectangle of size A by B. Let's work with an example. So my A and B are 16 and 6. Well, I'll just go ahead and try greedily, picking the largest tile I can and fit it in there. So, I'll try picking this 6 by 6 tile and, place it there on the left end. And then I'm saying, okay, I'm going to just go and tile the rest of it, the 10 by 6 grid that is left. So why is this okay? Why is this useful? Because we just argued that, the common divisor of 6 and 16 is the same as the common divisor of 6 and 10. And in particular, not just the common, because the common divisors are the same, in particular, the greatest among them is same. So the GCD is same. Right, so instead of looking at GCD of 6 and 16, I can just try to compute the GCD of 6 and 10. Okay, so this is what happened after I put this big tile, as big a tile as I could, square tile as I could on the left. And I try doing that again. I pick as big a tile as I can. So 6 is the largest I can go. So I'll take a 6 by 6 tile and remove that. So this just corresponds to removing 2 copies of 6 from 16, right? So again, as we saw, GCD of A and B is the same as GCD of A and B minus QA. And at this point, B minus QA, in this case here 4, is smaller than 6. So I cannot put another 6 by 6 tile on top of this anymore. But I'm going to continue looking at, I'm again thinking of tiling this thing as big a square tile as possible. I just go ahead and pick the largest square I can, which is a 4 by 4 square. And why is this interesting? Because what is left untiled now is a 4 by 2 grid, and GCD of 6 and 4 is the same as GCD of 2 and 4. So here, think of 4 as A and 6 as B in this equation here, right? So I just, I'm working with 6 minus 4, that is my 2 here. Okay, and then I try tiling with a 2 by 2 tile. I want to tile this grid. So I put in the first 2 by 2 tile, and I see I can put in one more. I put in the next one also, and then I'm done. I don't have any more tiles to cover. The grid is completely covered. So 2 is indeed the largest I could have obtained. So this corresponds to 2 divides 4, right? So remember we said if A divides B, GCD of A and B is A. So in this case, the GCD is 2. Okay, so this is Euclid's algorithm. At every step, you're given 2 numbers. You remove as many copies of the small number as you can from the large number. You'll be left with the remainder of the larger number. And then you recursively continue finding the GCD with those 2 numbers, the remainder and what used to be a smaller number. Now the remainder has become a smaller number. And you do this until you hit a point where A divides B, or one of them divides the other, and then the smaller number is the GCD, and you're done. And in fact, this algorithm that let you compute this 2 tells you a little bit more about 2. So let's see how we got this 2. By the way, so once you have this 2 by 2 grid, 2 by 2 square tile, that can tile this one, that it can also tile this one because it's this the same side here. And since it can tile this one and this one, it can tile this entire side, and therefore it can tile this square, and therefore it can tile this square, and so forth. Right? So it can be, this 2 by 2 square tile kind of from the picture. Also, it should be clear that it can tile the whole grid, but of course the argument is is this GCD of AB is the same as GCD of A, and the remainder of B divided by Q. So you can recover this 2, you can kind of trace how this 2 came about. That 2 came about because it was, I had a 6 by 4 grid and I removed 1 copy of 4 by 4. That's how I ended up with the 2 here, right? So 2 was 6 minus 4. And how did I get the 6 and 4? Originally I started with 6 and 16. So that 4 came about as 16 minus 2 copies of 6. And so I can just open that up and I'll see that, so this is 6 minus 16 minus 2 times 6. So that becomes plus 2 times 6. So 3 times 6 minus 16. So 18 minus 6. That's how I got the 2. Okay. So why is this interesting? That I'm writing the GCD as some combination of the original numbers 6 and 16 multiplied by some integers. So it's actually a very useful thing. This is a name, it's called Discrete identity. We'll see that in a bit. And this is just saying that, okay, you can always write the GCD of any 2 integers as an integer combination of those 2 integers. Integer combination means, multiply them by integers and add them together. Okay. So let me just, switch gears and go to another picture, which will be used to prove this. So, here it was a kind of proof by example, and as you can imagine, if I were to prove something like this, some sort of induction has to be there to reason about this recursive process that I, unrolled this this computation, this recursive computation of GCD many times. I kind of unrolled it backwards. So we'll see there will be some element of induction in how we will prove this theorem. Okay, and this, by the way, this algorithm. So you do this computation of GCD. That's called Euclid's GCD algorithm. And along the way, if you keep track of how these multiples were derived, and use that to write 2 as 3 times 6 minus 1 times 16. So computing this 3 and minus 1, so this U and V, doing that is called extended Euclidean algorithm. So it's just a little extra bookkeeping on top of this recursive algorithm. Okay. All right, so let me switch gears and do something which will let us prove this claim here. So here's a picture of a bunny sitting on a number line. Okay, so these little red notches here correspond to the numbers 0, 1, 2, 3, and so forth. And goes both ways infinitely. And this bunny has, it knows to hop, to jump, and there are two ways it can jump. It has a short jump and a long jump. Okay, so the length of these jumps are a and b. So there are some integers. Okay, that's how our bunny works. There are some integer lengths, and it could jump either way. It can hop left or right. Okay, so for instance, if let's pretend a and b are positive, then negative jumps. It can do something like say -3 times a. That would correspond to a left jump to the left, and 3 times a would be a jump. A will be 3 jumps to the right, right? And -3 times a will be 3 jumps to the left. 3a jumps, the short jumps, let's say. And the question is, okay, so it can keep bouncing around, jumping around. It can alternate between the A jumps and the B jumps. It can go right or left. And in the process, which all points or these notches can the bunny reach? Okay. So let's just uh, think about it. So after, if the bunny jumps, if it jumped a lot, and you looked at the total number of A hops it made, and let's say that total is U. So this could be a positive or negative number. It could have, say, if it jumped 3 times to the right and 10 times to the left, it's as good as jumping 7 times to the left. Right, so the order of the jumps don't matter to compute the total, final position it reached. So all I need to know is this net jumps, right? Whether it could be positive or negative. Um, so let's say that net number of A jumps is U, and the net number of B jumps is V. Then the bunny will be at the position A times U plus B times V. And what we are interested in is a set of points that can be written in this form, right? That is the answer to this question. So let's just define that set. So I'm defining it as L of AB. It's a set of all points, all integers, you can write as A times U plus B times V, where U and V themselves are integers. Okay. And let's look a little closer at this, set. I'm going to call it a lattice, or a one-dimensional lattice. So it's a general term for a set of points you can write as integer combinations of, more generally it could be integer combination of vectors in some higher dimensional space, but for us it's a one-dimensional space. So the A and B themselves are just integers for us, in fact. So first claim is that whichever point the bunny can reach, that point is a multiple of the GCD of A and B. Actually, it's not too hard to see. Take any point that the bunny can reach. So that is to say, it's AU plus BV for some integers U and B. Well, what do we know about the GCD? GCD is a common divisor for A and B. So I can write A as some multiple of G, so G is a GCD, and B also is a multiple of G, right? So AU plus BV looks like this GPU plus GQV, and I can take G out as a common factor, and X is therefore a multiple of G. Okay, so G divides X. That's all I was claiming, right? The GCD divides X. So that's an easy claim to see. Here is a more interesting claim that the GCD actually is a point that the bunny can reach. Okay, so I didn't tell you anything about this A and B. It could be arbitrary integers, but the GCD of A and B is a point that the bunny can reach. Okay, so actually instead of induction, we'll use well ordering, the principle of well ordering, and as we argued earlier, it's equivalent to induction. Okay, So principle of well ordering says if I give you a subset of positive integers, then it has a least element. So let me first define a subset of positive integers. So LAB has positive and negative integers. I look at its intersection with positive integers. So LAB intersect Z plus, okay? And I'll call this L plus, okay? Okay, so L plus is some positive, is a set of positive integers, and it's non-empty because, say A belongs to it, for instance, or minus A if A is negative. So let's say, I can apply the well ordering principle and say it has a least element. Let that least element be D. Now D is in this L plus AB, and therefore in LAB. So it has the form AU plus BB for some integers U and B. Okay. Also, I'm going to look at the remainder. So this is kind of what the GCD computation was also doing, right? So I'm going to look at the remainder of A with respect to D, okay, and let that remainder be R. So D, remember, is a positive integer, which allows me, is a particular not equal to 0, which allows me to invoke the quotient remainder theorem and write A as dq plus R, where R is strictly in this, strictly less than D, and it's non-negative. Okay, so what do I know about R? R is strictly less than D. So by definition of how I picked D, D is a least element, R cannot be in this set, right? Because R is strictly less than D, and D was supposed to be the least element in the set. So R cannot be in this set. On the other hand, R can be written as A minus DQ, right? And D itself is AU plus BV. So R can be written as, some A times 1 minus U plus B times minus V. Each of them has a factor Q also. So R can be, let me say that once more, R can be written as A times 1 minus QU plus B times minus QV. Okay, so some integer combination of A and B. Therefore, it is in the set LAB. But it's not just in the set LAB, it's also greater than or equal to 0. So it is non-negative. But it cannot be positive because then it would have been in L plus AB, and we just now said R is not in L plus AB. So the only way out is R has to be equal to 0. And what does R equal to 0 mean? R equal to 0 means that A is a multiple of D, okay, or D divides A. Similarly, there was nothing special about A here. I can do the same argument with B, and I'll get D divides B. So D divides both A and B. So it's a common divisor of A and B. And then by the definition of GCD, GCD is the largest common divisor. So D cannot be more than GCD. So D is less than or equal to GCD of A. But D was an element that started off, D was an element in L plus AB, therefore it's in LAB. And now I'm going to go back to claim 1, and it says, okay, in any element in LAB, right, is a multiple of the GCD. So GCD divides D. So we have a number D which is less than or equal to GCD, but GCD also divides that number.